So, welcome to the 20th lecture of graph theory. So, today we will look at a slightly different topic, of course, about the coloring problem, graph coloring problem. So, the material for this will be available in the graph theory textbook by USR Murthy and Bondi. Earlier I was mostly following Reinhard Distel's book. This is taken from Murthy and Bondi and Murthy's book. Here we are going to study certain polynomials which will help us understand the graph coloring problem. So, we are going to associate a polynomial with a graph. So, let G be a graph and the vertex set is V1, V2, V3 up to Vn, and we will define some variables x1, x2, xn corresponding to each vertex. We will associate a variable. Then the adjacency polynomial of the graph G is the multivariate polynomial, the polynomial in these n variables a g comma x equal to the product of xi minus xj, where this I j are Vi and Vj is an edge in G. So, what it means is, so you can take a small example. For instance, let us consider the simple, very simple example star. So, let me say this is V1 and I assigned a variable x1 to it, right, and it is V2, therefore x2 is assigned to it. V3, so I will have a variable x3 for that, and V4 variable x4 for that. Okay. Now, we have these edges V1, V4, V1, V3, V1, V2. So, our polynomial will correspond to these terms. First, for this edge we will have the term x1 minus x2, not x2 minus x1, because we are taking the smaller index first and the higher index next. I less than j is what we have. So, this edge will correspond to the term x1 minus x3, and this will correspond to the term x1 minus x4. So, what will be the polynomial, adjacency polynomial for this thing? Ag of x for this will be equal to x1 minus x2 into x1 minus x3 into x1 minus x4. This will be the polynomial for this, right. So, going back to this, so this is the way it is defined. So, our terms correspond to the terms, this xi minus xj terms correspond to edges Vi, Vj, and then of course xi comes earlier than xj if I less than j. That is the way this thing. So, how does this polynomial help? Why do we define this, and we say that why do we say that this is going to help us in understanding the graph coloring problem? See, you can see that if there is a coloring, proper coloring, vertex coloring of the graph, then if there is a proper vertex coloring of the graph, then if we consider these colors as numbers, right, and then this if you substitute xi with the color given to the ith vertex, then we know that because whenever I and j is an edge, xi and xj will not get the same color, xi minus xj will not become 0. So, no term in this polynomial xi minus xj will become 0. Therefore, if you multiply these terms, what you get will be a non-zero value, right. This will evaluate to non-zero if you assign the value of the color to the corresponding vertex. So, a coloring would corresponds to solutions of so the values for x1, x2, x3 etc., such that the when you substitute those values, the polynomial evaluates to a non-zero value. So, if it evaluates a 0 value, it is not a coloring, or in other words, any solutions, any assignments of values to exercise such that this polynomial evaluates to a non-zero value will be a valid coloring. Why? Proper coloring. Why? Because even in one case xi minus xj happens to be 0, the polynomial will have to evaluate 0. That means xi can never be equal to xj if ij is an edge. So, this is why this polynomial becomes interesting for the case of the graph coloring, vertex coloring problem. So, that is why we decide to study this polynomial, right. And now, okay, so that much is okay, but this is more or less a quick observation, but how can we understand this polynomial better? Of course, one obvious way is to expand it, right. So, you want to expand it and look at what kind of terms will come, right. So, for instance, in our case, let us look at x1 minus x2 into x1 minus x3 into x1 minus x4. This can be expanded. So, like so when you expand, how do we get it? You take one term from here, one term from here, one term from here. This is first is x1 cube plus then one term from here, one term from here, and then other term from here. So, x1 square into x4. What is the sign of that? Because this is 2 pluses and this is minus, therefore, this will be minus. This is minus term, and then now one term from here. Here you can change, the second term can be changed, and the third term. So, again x1 square into x3. So, this is minus, right. So, then we can take say, so like that you can generate all the terms. How many terms you can generate? Because there are two possibility of taking terms here. So, the picking up the multiplier from here. So, therefore, and also there are how many equations equal to the number of edges terms are there. So, m is the number of edges. If m is the number of edges, then we will have 2 to the power m terms. 2 to the power m terms will come. So, for instance, you could have picked up here this minus x2, and you could have picked up this from here, and you could have picked up this from here. That is minus x2 and minus x4 and a plus x1 will make a total plus. So, this will be x2, x1, x4, this kind of terms. Right. So, you see that, so corresponding to each edge we can pick up a term, and then we get monomials, 2 raised to m different monomials like that. So, what does these monomials correspond to? So, each monomial in the expansion has this sequence x1, x1, x1 here and x4, here x2, x3, x4, this is x1, x1, x3, so like that, and also a sign. There are two things, a sign and the term itself, the constituent things. So, but first let us try to explain this monomial, the sequence of variables that we see there, like x1 square, x3, x2, x1, x4 like that. So, for instance, let us look at this term x2, x1, x4. That means we picked up this x1, x2, the second term. You know, always these terms are written, the first term is smaller and the smaller index, the first term has the smaller index and the second term has the higher index. So, I picked up the second term. So, and we can try to, so we will go back to that picture here. In this, for this edge we decided to pick the second term. So, we can orient this edge from the second term to the first term, right. If the this, maybe we can give a direction to indicate that essentially this was picked up, right, second term was picked up. So, if on the other hand for the next, in the next case, so here this is your first term is picked up, right. This, so in that case we can say here the arrow can be put like this. It means that the first term was picked up. The arrow is the tail of the once you give an arrow to this, so the tail is essentially the term which we have picked up, the first or second, or in other words the lower or the higher, right. And now this one x4. So, if you go to the third term, so here this third edge, so here x4 is picked up, that means we have to orient it this way, direction backward. So, essentially you can see that the way we have picked up the variables from each of the terms, each of the terms in the product corresponds to giving an orientation for each edge. So, finally, when you make a monomial, that monomial corresponds to an orientation of the total graph, giving some direction to each edge of the graph. That is what it happens. Now, how will we interpret the degree of a vertex? For instance, here we see that the out degree is 1. So, that means x1 has occurred just once in that term. So, here we see that the out degree of this thing is 1. So, that means x2 has occurred just once. Similarly, here the out degree is 1. So, on the other hand, if I had picked up another term, say for instance, sorry, so if I had picked up x1 square x4, so x1 square x4, then so that means here x1 is picked up, x1 is picked up, x4 is picked up in the third one. So, that will look like, so I can mark it with green. So, here x1 square x4, the first is x1 picked up, that means the direction is in the opposite way here, and then here it is picked up this way, here it is picked up this way. So, x1's out degree with respect to this orientation is 2, that is why x1 square has come, and x2 right, x2 didn't x2 didn't get any degree. So, the x3 didn't get any degree, out degree. So, therefore, it's not appearing in that term. Here x4 has one appearance, therefore, x4 has a degree 1. So, essentially to summarize, so each monomial in the expansion corresponds to an orientation, and this orientation is with respect to how we picked up terms from each constituent term of the product, either the first term or the second term. We gave the direction to the edges based on that, right. So, now that is the way the orientations are, all possible orientations, 2 raised to m possible orientations are there, they corresponds to the 2 raised to m possible monomials that appear here, right. Now, the next thing is to understand what signs we can get. So, we can see that the same term, say x1 square x3, so maybe x1 square something else can come several times irrespective of see in this graph it may not happen, but in some other graphs you could have observed that the same term can repeat several times, because what matters is if with respect to an orientation a particular vertex, say ith vertex has 2 outgoing edges from that, appear 2 times in the monomial. So, xi square will come there, right. So, if the degree out degree sequence with of 2 different orientations were same, then the terms will read same, they will read same, they will be same. So, but then only thing is the sign may not be same, the signs may be different. It is possible that one of them may get a positive sign, the other may get a negative sign. So, though there are 2 raised to m terms, some of them are same terms, but possibly with different signs, then they may add up to make a 0, that means they may cancel out. So, finally, even after if you really do the cancellations, then the expansion may not have all the 2 raised to m terms, right. So, they may some of the terms may be lost. It is also possible that in some cases they may add up and make a term like 2 times x1, x2, x3 something, it is also possible. So, it is important to understand that these terms also have signs. So, but then now we have to understand what the sign of a monomial will be with. So, in terms of the orientation which corresponds to that monomial. So, that is also not very difficult to understand, because you see whenever we are orienting the edge from the lower to the higher, that means we are picking up the positive term. When we are orienting the edge from the higher to the lower, we are actually picking up the negative term. Therefore, in the orientation we will look at each edge, each directed edge, and see whether the direction is from the lower to the higher or higher to the lower. Accordingly, we will say that that edge in that orientation, that edge has a plus sign or a minus sign, and now we will multiply all these signs together, and then we say that that is the sign of the orientation. That will definitely correspond to the sign of the monomial in the expansion, right. So, we can define it this way: d be an orientation of G, then sigma of D, that means the sign of the orientation can be defined as the product of the signs of the directed edges in that orientation. For each edge in the directed edge set of the directed graph. So, you have to define a sign and then multiply the signs, that is all. So, how do we define the sign of a directed edge? So, sigma of A being a directed edge is equal to plus 1 if A is equal to V I V j, where I less than j, that is directed from the smaller index to the higher index. Similarly, it will be negative if it is in the edge is going from the higher index to the lower index. So, this is the thing. So, now so you can pick up a particular degree sequence, out degree sequence, that means the first vertex, the V1 has degree D1, out degree D1, second vertex has out degree D2, third vertex has out degree D3, and the nth vertex has out degree Dn. That is a degree sequence, out degree sequence of a this thing. It is possible that given a particular orientation of the given graph, and we are given an undirected graph G. So, some orientation is given to the edges, some direction is given to the edges. Now, with respect to this orientation, we can write down the degree sequence. V1 got degree D1, V2 got degree D2, like that we can write down. But it is not true that each different orientations have different degree sequences. It is possible that 2 different orientations may have the same degree sequence. So, we collect, given a particular degree sequence D1, D2, Dn, we collect all the orientations corresponding to that, that means all the orientations with that particular degree sequence, and then we consider the signs of each of them, we sum up. This is the sign of the degree sequence, that particular out degree sequence has this sign W of D equal to sigma sum of the signs of the signs of the, here this is a mistake. So, it says that signs of the sigma of big D here. So, signs of the orientations with that particular degree sequence. What it corresponds to in the expansion of that polynomial, that we have this particular terms, that x 1 raised to d 1, x 2 raised to d 2, x 3 raised to d 3. So, x n raised to d n, this is what correspond to the degree sequence. There are several such terms. So, finally, what will be the, when you add them up, what will be the coefficients, because some of them are negative, some of them are positive. So, you are just adding those coefficients together to get the total coefficients, that is the W of t. Because for a given term, the term can only be distinguished by looking at the powers on x right, x 1 raised to what, x 2 raised to what, that will only be distinguishing between two different monomials. So, we can collect them together and then the coefficients are added together, and that corresponds to summing up the signs of the corresponding orientations, that is all it says. So, now the next thing is to say that, for instance, you can say x raised to d, d being a degree sequence, d is equal to, so d is essentially this d 1, d 2, d n, right, and then this x is some the variable x 1, x 2, x 3, the tuple, n tuple of variables. So, that can be written, that is a short form of a monomial, in fact, x 1 raised to d 1, x 2 raised to d 2, x 3 raised to d 3, x n raised to d n. This monomial's short form is x raised to d. Then we can write this polynomial a g of x as the sum over all possible degree sequences, the weight of the degree sequence, that is the sign of the degree sequence, into, sorry, it is the weight of the degree sequence, it need not be plus or minus 1, it can be something else also, right, weight of the degree sequence into that x raised to d, that is the monomial. This is the way we can write. See, what is the good thing about writing like this, because it would be much easier to understand when this can be non-zero with respect to the orientations, when you want to study this polynomial with respect to the orientations. See, as we have seen, what we are interested in is in some way when these polynomials evaluate to non-zero values, right, that is what correspond to the proper vertex coloring of the corresponding graph, right. Now, to understand that, we have expressed this polynomial as a sum of see this with respect to this degree sequences, we have expressed as a sum the weight of the degree sequence into x raised to d. And so, the now we can always ask, suppose given a degree sequence, you can consider all the possible orientations with the degree sequence, and if I sum up the signs of that degree sequence, will it be negative or positive? Such questions, or will it be 0? Such questions can be asked, right. So, this is what we are going to make use of in the later proofs. So, now we want, see, our intention is to use this polynomial to show a result for the list coloring of graphs. What we will show is, if G is given and it so happens that there exists a orientation of the graph, the edges of the graph, in such a way that there are no directed odd cycles with respect to this orientation, and also that the out degree of each vertex is strictly less than the list size of list size of that vertex. So, given a vertex, the cardinality of the list, the size of the list is strictly bigger than the out degree. In that case, we can always come up with an acyclic edge coloring. So, we have studied a particular some theorem like that earlier. We have seen that if the degeneracy is small, we can do that. For instance, if there is an ordering of the vertices and the higher numbered neighbors are small, then we can do a coloring, right. We can do the coloring from the list. And also in the last class we studied that if this second condition is again same. Suppose the out degree of each vertex is strictly smaller than the cardinality of the list, plus the property that every induced subgraph has a kernel, every induced subgraph for the directed graph has a kernel, then also like that if we can get an orientation for the graph, then also we can get it. Here there is a different, slightly different thing. We are saying that the same condition, that is the list should be such that the cardinality is strictly more than the out degree, plus the other condition is just that there are no odd cycles with respect to that orientation. If we can find even one orientation which avoids odd cycles, that is enough. So, that is pretty interesting, much maybe much more interesting than the statement we came up with yesterday. So, though we used it for proving the bipartite graphs, right, in the this thing. So, here also because here also we only want to avoid the odd cycles. So, of course we can think about, because bipartite graphs does not even have an odd cycle. So, an orientation cannot bring odd cycles there, right. So, that would lead to that, this also will lead to that, right. So, then here we are going to use some techniques. So, we have to develop these tools first. So, the look at this thing, let f be a non-zero polynomial over a field f, right. Let f be a non-zero polynomial over a field f in the variables x1, x2, xn of degree di in xi for each I, and let Li be a set of di plus 1 elements of f for 1 less than equal to I less than equal to n. Then there exists a t element of L1 cross L2 cross up to Ln such that f of t not equal to 0, right. See, this statement is very familiar when we restrict our x to be just one variable. I mean, if the polynomial is just in one variable, that is, if there is only one variable, it is like saying that if you give me d plus 1, d being the degree of the polynomial, that means x appears up to x raised to d and not x raised to d plus 1 or more, then you can only have d distinct roots. If there are d plus 1 distinct values, one of them when substituted for x will evaluate to a non-zero value, that will not be a root, because there are only at most d distinct roots. This is a famous theorem, the fundamental theorem of algebra. So, therefore, we can so we are familiar with it, but the only thing is we want to generalize it to a several variable case. So, to do this thing, what we can do is, yeah. So, you can consider this function, so sorry, this polynomial f in x1 comma x2 comma x3 comma xn. So, this polynomial in this polynomial we can separate this xn, and in fact it can be expressed as a polynomial in xn alone, where the coefficients are essentially polynomials in the remaining variables x1, x2 up to xn minus 1. So, we will say f1 is a polynomial in up to here, and then so x1 xn raised to 1, right. So, and so we can say it is f0 into plus f1 of x1 comma xn minus 1 into xn raised to 1. So, f2 of x1 to xn minus 1 into xn raised to 2 and so on. So, fn into sorry. So, essentially we are saying that the degree up to which it can go is say f d I d dn, right, f dn. So, x1 to xn minus 1 into xn raised to dn. So, we are restricting the degree of dn to be degree of xn to be dn, degree of x1 is d1, degree of x2 is d2 and so on, right. Now, we know that by because the one variable case is familiar, it is known. So, therefore, we can use this to infer that. So, if x n has d n plus 1, so if we are given d n plus 1 distinct values, then x n can get a value such that if this polynomial was non-zero, if the total polynomial was non-zero, then it evaluates a non-zero value. So, so why is this polynomial non-zero? Because this f 0 x n minus 1, so they all will become non-zero for some values, right, by induction, right. So, therefore, so since f 0, so each of these polynomials will get certain values. So, we can make use of the induction hypothesis and so attach, therefore, by induction we will get that if there is a list of values for x 1 L 1 and if there is a list of values for L 2 for x 2 and if there is a list of values L n for x n, then we can pick up the some value from this T L 1 cross L 2 cross L n such that the when you substitute those values in the polynomial, that evaluates to be non-zero. That is that is what will come, isn't it? So, okay. Now, we can see that okay. So, this is the this is just proved by induction, by just using the 1, then we will generalize it to 2 and then it is to 3. So, we know that when we can always make one of these polynomials non-zero f 1 f 2 and therefore, the total polynomial will become non-zero and then we can add the selection from L n also with respect to that and then we will get the total. So, then the next one is a generalization of, or not a generalization, it's we want to, because if you want to use it, we want to convert into a convenient form. So, we will make some minor modifications, it is called the combinatorial Nullstellensatz. So, the it is like this. So, let f be a polynomial over a field f in the variables, that is x 1, x 2, x n, and suppose that the total degree of f is I equal to 1 to n d I and that the coefficients in f of x I d I, the product of the monomial, is non-zero. So, here the difference is that we are not committing that this x 1's highest possible degree is d 1, neither are we saying that x 2's highest degree is d 2. In the earlier case we had told like that, but here we are only saying that the total degree is going to be, when you sum up the degrees of each monomial, it is going to be at is I equal to 1 to n d I. So, that is the sum of the d i's, but individually some of them can be bigger than the corresponding d I, though overall the total will remain to be I equal to 1 to n sum d I. And the another thing is, we are not saying that the polynomial, as such the polynomial is a non-zero polynomial, but there is one term in it, namely the x I raised to d I term, that is x 1 to the power d 1 into x 2 to the power d 2 into x n to the power d n. This term's coefficient will be non-zero. So, these are the two conditions you are saying. So, and then you also should understand what is d I. So, d I is some parameter associated with each variable. X 1 has an associated parameter d I at d 1 and x 2 has an associate parameter d 2, that is an integer. So, then what we are going to do is, so we have to pick up a list for each variable Li. For xi we will have a list Li. So that we want to pick a value from this list for xi, and the cardinality of Li will be di plus 1, that is the relevance of di, right. So, that is the way we are associating di to xi. So, the xi is a variable, we are saying that it has a list of values associated with it or which are allowed for it, and its cardinality is di plus 1. Now, compared to the earlier statement, here we are actually in some terms xi may have a degree greater than di, but the total degree will remain same. So, I is equal to 1 to n, sorry, the total degree is sum of I equal to 1 to n di, and the other condition is just that if you, because we know these values d1, d2, d3 etc., and if you consider this particular term x1 raised to d1, x2 raised to d2, x3 raised to d3, namely x n raised to dn, this term's coefficient will be non-zero. So, these are the only conditions. If these two conditions are satisfied, then we can again pick up values from L1 for a value from L1 for x1, a value from L2 for Lx2 and so on, such that the total, when you substitute these values, the polynomial evaluates a non-zero value. Then there exists a t element of L1 cross L2 cross Ln such that f of t not equal to 0. This is what it says. So, to prove this thing, we can, what we can do is, so we will use the earlier statement, we will reduce this to that. So, this is the way. So, our problem is that, so f is not a polynomial as we described in the earlier statement. So, it may have higher terms in xi's highest degree may be more than di, therefore, we have to reduce it. So, we first will define some terms called some new polynomials called fi. So, what will be fi? Fi will be just from the list Li, we will take all the values. So, we will define xi minus t sigma t from Li, right. So, we will create these terms xi minus t. So, there are essentially cardinality. So, cardinality of Li is essentially di plus 1, right. So, this will be a polynomial in xi raised to di plus 1. The degree of this polynomial will be xi raised to di plus 1. So, and the first term, it will be the first term, it will be a long term. So, we can write fi as xi raised to di plus 1 plus some gi. So, gi and g, so such that the gi will be of degree di, right. So, therefore, we can say that fi equal to gi raised to di, and now the good thing about this is if you substitute any value from Li in this f in this. So, for any t element of Li, so fi of t will be equal to 0, that means this side will evaluate to 0. So, gi of t raised to di plus 1 will be equal to minus gi minus gi. So, this will come for any t we selected from this thing. Now, what will we do? We will go to f, we will consider the polynomial f, and whenever we get we see x raised to, suppose some xi raised to di plus 1, we will, so it can be right xi raised to d plus 1 into xi raised to something else, right, some smaller term. So, we can pick up this separate this and substitute by minus g. So, then we will repeatedly substitute by minus g and multiply again. So, because we are substituting with a lower a polynomial with a lower degree, the degree will reduce because see because initially it was di plus 1 degree, then only lower degree terms are there, xi raised to di and below are there, the degree will reduce. So, finally, if you keep on repeatedly doing it, finally we will end up with a polynomial g which is produced. So, this is gi. So, produced from f by these repeated substitutions, and we will end up with by getting a polynomial where all the degrees of xi is di. Similarly, that means x1's degree will be at most in this polynomial gi, x1's degree will be at most d1, and then x2's degree will be at most d2, and so on. This is what we wanted to, if you want to make use of the other theorem, we want this condition. So, in this statement we were not imposing that xi its degree should be di alone, but because we are allowing higher degree also, but now we reduced it to di, right. Now, the final polynomial will have degree only this much. And the second point is, in fact, we only need to worry about this new polynomial g as far as substitution when the values from this lis li is substituted for xi, because we are always substituting xi to the power di plus 1 with minus g. But we know that essentially if we substitute any value from li to this xi, then essentially that value will be equal to gi of t also, what we substituted. Why? Because we know that fi is equal to xi raised to d plus 1 plus gi. So, gi, and then for any value of t from the list li, this will vanish 0 and this will be equal to minus gi. So, then we can when we evaluate in g by substituting a value for xi from the list li, so g and f will evaluate same. So, we will have g of t equal to f of t if t is picked up from L1 cross L2 cross, so LD. This is what if each xi got a value corresponding value from Li, then if you substitute in gi or g or t, does not matter, right. So, and now so in other words, to show that f of t can become non-zero for a selection of values from L1, L2, LD for the corresponding variables, we only have to show that g of t, g will become non-zero for a selection of values for xi gets this value from Li, right, because these are for those such values these are same, right. So, that is, but then now can we use the earlier statement? Even now we cannot use, because we have to also show that it is a non-zero polynomial, isn't it? Is it a non-zero polynomial? So, it is a because the non-zero polynomial comes because if you consider this particular term x 1 raised to d1, x 2 raised to d2 and x n raised to dn, this is not at all changed, right. So, therefore, they will so, and this what is the total degree of this thing? This total degree is sigma di, I is equal to 1 to n, right. And if you look at every other term, their degree has reduced, right. Their degree has reduced, because originally in f we had a non-zero coefficient for this thing, and all other polynomials got its degree reduced, because in some cases it may be di either reduced or retained same, because if it is already small then we do not have to worry, but on the other hand if it was like x1 raised to d1 plus something some k, and then for somewhere else x2 raised d2 minus k, adjusting like that, then we know that this got reduced, therefore, the overall degree came down for that term. So, for each term, so therefore, this is the highest degree term, and therefore, it means that this is a non-zero term. Therefore, the polynomial has to evaluate a non-zero value for some selection of xi's, because anyway there is a term which will dominate, right. So, therefore, we can say that the resulting polynomial is a non-zero polynomial. So, why did we do that? Because if we want to apply the other theorem, the earlier theorem, we need, earlier theorem means this theorem, the earlier theorem, we need it to be non-zero. So, we have g as a non-zero polynomial, and also the degree of each xi is di, right. Therefore, from the list Li we can select values for xi such that f of t will g of t will evaluate not to 0, and therefore, the corresponding f also will not evaluate to 0. That is the way we construct it. So, because we constructed g from f in such a way that when if we are selecting values from the Li, the g of t and f of t will be same. Now, we got a t from selecting from Li such that d of t is not equal to 0, then f of t also has to be non-zero. So, this is what. So, why did we do all this thing? How are we going to make use of this thing? So, as I mentioned before, our intention is to show that if this is the theorem we want to show finally, if G is a graph and if there is an orientation of G without directed out cycles, then G is D plus 1 least colorable, where D is the out degree sequence of G, D is the out degree sequence of G, right. So, this is what we wanted to show. So, now to do this thing, so how are we going to relate this with the polynomial and the combinatorial Nullstellar and SATs? You can see that the essentially this list Li corresponds to the list of the list coloring problem. So, in the list coloring problem we are given a graph and each vertex is given a list of colors, we can say the list of values. So, you know that each vertex is associated with a variable. So, it is like asking that variable to pick up a value from the list, namely the list of colors, which happens to be the list of numbers, that list, and in such a way that the polynomial does not evaluate to be 0. Why? If the polynomial does not evaluate to 0, it means that none of the xi minus xj terms have become 0. Remember, the original, the polynomial was the product of xi minus xj's, where I and j are edge, I comma j is an edge, right, vi comma vj is an edge. So, none of the edges turned out to be 0, that means turned out to give a term which evaluates to 0. So, xi was always not equal to xj, that means it is a coloring of the graph, right. So, if you can assign values to xi's from the given list, then that means it is list colorable, it is list colorable. Now, the combinatorial Nullstellar SAT says you can associate values to these variables from the given list. So, if certain conditions are known, for instance, so the cardinality of the Li, so let us say that is di plus 1. Now, we have to make sure that the degree, the total degree of the corresponding polynomial, is at most the sum of di's, at most the sum of di's. So, which essentially is true, because if you take any monomial, right, it corresponds to some orientation, and this sum of degrees essentially will be the number of edges, right, number of directed edges, because each directed edge will essentially contribute only one term, right, because it corresponds to the degree of contributes only one term. So, therefore, essentially it is the total number of directed edges. So, therefore, the total is essentially for any directed degree it is sigma di's, right. So, then the only thing is if you can find out an orientation in such a way that, so the second condition, that means the x1 raised to d1, x2 raised to d2, x3 raised to d3, that term, the corresponding term is has a non-zero coefficient. That is the only thing we will need. So, you can see that in the combinatorial Nullstellensatz we had these two conditions, right. The one is the total degree has to be sigma I equal to 1 to n, that means outcome. So, that is going to be the same for all orientations. So, therefore, we cannot so we want to get the convenient split up. So, we want to get a degree sequence in such a way that the corresponding Lis, right, Li has degree strictly greater than di, some degree sequence like that. Suppose you can find a degree sequence for an orientation. If you can get an orientation with such a degree sequence that the corresponding out degree is strictly less than the di, that is what, that is all we need there. And second, this one, that means the coefficient of xi is to di has to be non-zero. If we can show that, then we have a selection from the list, is what thing. So, which will give allow us to list color, right. So, which will allow us to make the polynomial evaluate a non-zero value, that means which will allow us to list color the graph, right. So, therefore, we essentially we only have to prove that. So, suppose there is a degree sequence, right. So, this is the statement we want to say. So, suppose this degree sequence that the orientation, the corresponding term monomial x, the or the x1 raised to d1, x2 raised to d2, x3, x1 raised to dn has a non-zero coefficient in it. The weight of that w of d, that weight of that degree sequence happens to be non-zero. Such an orientation if we can find, then we can say that it is list colorable, right. List colorable as long as the lists are just at least one more than the corresponding out degree of each vertex with respect to the degree sequence. So, now how do we say that this term will evaluate to a non-zero term? So, here is the reason, because we are saying that if, so this is the condition, one condition which will ensure that, suppose there are no odd cycle with respect to that orientation, then corresponding monomials for each, so for instance for that particular degree sequence, any of such any such orientation with the same degree sequence has to add up, because there will not be anything to cancel, because they will always have the same sequence. This is what the statement says. So, how do we show this thing? So, suppose d dash is an orientation of G with out degree sequence T, and the sign of two orientations will happen to be same if and only if the difference, I mean AD minus AD minus, so there are some common edges between the two of them, but the remaining edges if you consider, so in A of t, in one of them, in fact, because the total number of directed edges is same, they essentially the total number of edges. So, either you consider AD minus AD bar or AD minus AD, it is going to be the same value. So, if this is an even thing, then we can say that the signs are going to be same, because the edges in the intersection of which edges belonging to both the orientations, they will anyway contribute similarly. The other things contribute, like if you consider an edge d, the contribution to d, if it is plus, the contribution to d plus d dash will be minus, right. If it contributes plus to d, it will be contributing to minus. So, if you keep on considering, so if you write down the edges E1, then E2, E1, E2, E2 like that, and the first contribution makes it, the first time when I consider it is plus and minus, then the next time it is again plus and minus, it will come back to the to equal sign, then the next time again multiplication will make it two different signs, again next multiplication will make it same sign. So, if you keep doing this, then you can easily see that if it is even number of edges out which are not in the intersection, that means AD minus AD bar, even number of edges, direct edges, then definitely the signs have to be the same, right. So, so that is what we need. So, now if D has no directed odd cycles, then all orientations of G without degree sequence D has to be the same sign. Why is it so? Because you consider any other degree sequence and you remove the intersection part, and now because they have for when you look at each vertex, the they have different signs and therefore incoming degree and outgoing degree has to be equal. I think we will explain this part, it requires some subtleties. So, we will explain this in the next class. So, we will continue with the polynomials related to coloring in the next class. So, thank you.